So when I say the name Galileo Galilei, what picture pops into your head? For most of us, it's this lone genius, right? Standing against the world, an icon of the scientific revolution. But what if the most famous stories we all know about him, the ones that basically define his legend, are more myth than they are reality? Let's dig in and try to separate the actual man from the legend.
Yes, this story. This is the one we all learned in school. The super dramatic scene at the Leaning Tower of Pisa. He's got two objects, one heavy, one light, and in front of all these skeptical professors, he drops them, and they both hit the ground at the exact same time. It's the ultimate scientific mic drop, completely shattering Aristotle's theory of gravity that had stood for centuries. It's a perfect story, maybe a little too perfect.
And here's the thing, there's no account from Galileo himself that this ever actually happened, not a single one. So where in the world did this iconic story come from? And if he wasn't doing that, what was he really up to?
To understand the real man, we first have to carefully, piece by piece, deconstruct the legend. And the very first piece that has to go is his most famous and, as it turns out, most likely fictional experiment.
Okay, so check out this timeline, because it really puts the whole legend in a fascinating new light. First off, the idea that objects of different weights fall at the same speed? Totally not new. A guy named John Philoponus was arguing this 1,000 years before Galileo. Then, in 1586, just before Galileo supposedly did his thing, a man named Simon Stevin actually did drop 2 lead balls from a tower in Delft and, published the results. And get this, the story we all attribute to Galileo, it only shows up for the first time in a biography written by his student Vincenzo Viviani, over a decade after Galileo had already died.
So where does that leave us? Well, the historical consensus has pretty much shifted. Most historians now are convinced this legendary event was actually a thought experiment, a brilliant exercise in pure logic, but not some big public spectacle. The power was in the idea itself, not necessarily in the action.
So, if Galileo wasn't dropping things off of towers, what was he doing? Well, this is where it gets really interesting, because the reality is, frankly, way more complex and a whole lot cooler. This is where the real work was happening. You see, freefall was just too darn fast to measure accurately with the tech they had back then. I mean, they didn't have stopwatches or slow-mo cameras. So Galileo had this absolutely brilliant idea. He decided to dilute gravity. By rolling a ball down a very gentle incline, he could slow the whole process of acceleration way, way down, enough that he could study it meticulously using things like water clocks or even just his own pulse.
And this slide right here, this gets to the absolute heart of the difference between science as a legend and science as it's actually practiced. The myth is this one, clean, eureka moment. But the reality? Oh, it was grunt work. We're talking hundreds of repeated, careful trials. Measuring the water that flowed out of a container to time the ball's descent, trying to find that hidden mathematical link between distance and the square of time. It's messy, it's repetitive, but that's how real discoveries usually get made.
His work with pendulums tells a pretty similar story. For decades, he was just fascinated by them, trying to prove this one very specific property, and it was anything but a simple, straightforward observation.
He was obsessed with this idea called isochronism. Basically, the theory is that the time it takes for a pendulum to complete one full swing is always constant, whether it's a huge, wide swing or a tiny little one. He thought this was an admirable property, but he could never quite get his experiments to demonstrate it perfectly. And now we know why. It turns out simple pendulums aren't actually isochronous. The real world is always just a little bit messier than our perfect theories.
This contrast really says it all, doesn't it? The diagram on the left, that's the inclined plane, a nice, clean, controlled experiment designed to isolate just one variable. The diagram on the right shows the actual, incredibly complex motion of a real-world pendulum. It just perfectly highlights the difference between creating an ideal system to test a theory and trying to understand a natural phenomenon with all its messy, subtle imperfections.
But Galileo's genius wasn't just in his physical experiments. Nope, some of his most powerful, most elegant proofs took place entirely inside his own head.
Okay, stick with me, because this is pure brilliance. Forget the tower. This is how Galileo really dismantled Aristotle's theory, using nothing but logic. So, follow the steps. Step 1, let's assume Aristotle is right that heavy objects fall faster. Step 2, tie a heavy stone and a light stone together. So what happens? Well, the light stone should act like a parachute and slow the heavy one down, right? So the pair falls slower. But, and here's the genius part,
The two stones tied together are heavier than the heavy stone alone, so according to the same rule, they should fall faster. You can't have it both ways. It's a logical contradiction, which means the initial assumption that weight determines speed has to be wrong. Boom, proved it without lifting a single stone.
And he used this exact same method to tackle even bigger questions. In this famous thought experiment, he asks you to imagine you're in a windowless cabin on a ship that's moving perfectly smoothly. And inside with you, there are fish swimming in a bowl, butterflies flying around. Could you tell if the ship was moving or just standing still?
The answer, and this is profound, is no. You couldn't tell the difference. His point was that uniform motion is relative. This was an incredibly powerful counter-argument to people who said, well, if the Earth were spinning, we'd feel it. We'd be blown off. Galileo argued that no, we wouldn't, because we, the air, and everything around us are all moving together, just like the flies in the ship's cabin.
So, why do we do it? Why do we cling to these simple myths about the tower and the telescope instead of these much more complex and honestly more interesting truths? Well, understanding that tells us a whole lot about how we think about science itself.
Here's a little dose of reality that really complicates the simple hero story. This table shows how accurate different models of the cosmos were at predicting the path of Mercury in 1631. And look at this. The best model was Kepler's, with his elliptical orbits. Galileo's preferred Copernican model, with its perfect circles, was actually worse than the old Earth-centered Ptolemaic model it was supposed to replace. Science is rarely a clean victory of right over wrong. It's often messy.
And the myths just keep on piling up. He didn't invent the telescope. He was just a brilliant early adopter who made huge improvements. He wasn't thrown in a dungeon. His prison during his trial was actually a 5-room apartment overlooking the Vatican Gardens. And he didn't definitively prove the Earth orbits the sun. He gave some really powerful evidence, for sure, but the final proof would have to wait.
The reason these myths stick around is, well, it's pretty simple. We love a good story. We much prefer the image of a lone genius having a sudden flash of insight over the far more common reality of science, a slow, difficult, messy, and often collaborative process of trial and error and tiny little steps forward.
And all of this leaves us with a final thought. Learning the real story of Galileo isn't about diminishing his genius at all. If anything, it's about appreciating it for what it truly was. But it also forces us to ask a really critical question. What other clean, simple, and perfect stories about science and history are we all just taking for granted today?